Hypothalamus Artificial Intelligence, HI, presents his research project. OPTEX GPU, the Artificial Brain Solver. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: Neocortex, Hypothalamus, and Hippocampus. This evolution may be summarized as the shift from artificial intelligence to augmented artificial intelligence. The artificial brains is the evolution of DSS under the Industry 4.0 revolution that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by OPTEX, the HI's cognitive robot, using the models that traditionally make up a decision support system. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, and its marketing process. The current state involves the integration of edge computing and cloud computing to implement highly complex mathematical models. For several years now, the mixture of computers and algorithms has been a fact thanks to the evolution of parallel mathematical thinking, the basis of artificial brains. Computing is evolving by leaps and bounds, which is giving rise to new visions of computing solutions, in this case based on specialized, low-cost, high-performance devices. This is the case of the Graphics Processing Unit, GPU, originally called array processors, an electronic circuit that can perform mathematical matrix calculations at high speed. And the case of the Jetson Orin Nano Super Developer Kit designed to accelerate the development of AI applications on embedded devices. It can be used for a wide range of applications, including image and video processing, robotics, IoT, and cloud-based AI, producing high-performance computing and low power consumption. This new way makes it possible to build computers composed of swarms of integrated smart devices such as GPUs, and GPUs, low-cost devices, combined with CPU clusters, allow the construction of low-cost supercomputers, which can use more elementary supercomputers than supersolvers. AI application devices. This implies that applications are deployed using intelligent devices based on the symmetrical atomization of systems and/or processes. As is the case with GPT-based artificial intelligence. This will give greater computing power to current artificial intelligence. According to scientist Jeff Hawkins, everything indicates that the structure and joint functioning of the neocortex and hypothalamus is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. The objective is to integrate the information from the artificial cortex with the communications and actions that the artificial hypothalamus must perform. The greatest advantage of mathematical artificial neurons is that they represent clearly defined objects within a system, that communicate with each other through fully known mathematical laws, and that they comply with laws with transitivity and divisibility laws, in such a way that a system can be atomized, to the level of knowledge that the scientist on duty has. This process leads to the atomization of the system, so that a problem of large dimensionality becomes a large number of problems of very low dimensionality. HI investigates the implementation of artificial brains based on smart devices specialized in solving optimization problems. This possibility can be focused on the implementation of the simplex method, which is the central algorithm around which all the different formats are solved. In 1978, Jesus Velasquez Bermudez, in his first company, PDC Ingeniería, developed an optimization solver in Fortran, for a ModComp Classic 7870 computer. Due to computational limitations, many advanced ideas were used that will be of great use in the design of OPTEX GPU. The main technological developments of optimization carried out in PDC were: development of a bounded primal dual simplex algorithm, PDC primal dual, with multipricing, inverse of the base in the form of product, and handling of the A matrix in compact constraint blocks, using dispersed matrix methodologies. Implementation of the pivot and complement heuristics to solve mixed integer programming, MIP, problems. Implementation of the Bender's partition and decomposition algorithm, using a variation of the PDC primal dual method, to handle Bender's cuts as a dense matrix, and compact matrix generation from relational databases in Fortran. There are two versions of the simplex method, the standard and the revised. The revised method is generally more efficient than the standard for large linear programming problems associated with sparse matrices, but for dense problems, the two approaches are equivalent. Dense problems occur in many important domains. For example, the cutting planes of Bender's and Dantzig-Wolff result in complete hyperdense problems, in which the version standard is faster. This led the PDC primal dual algorithm to handle these aspects differentially, increasing speed and reducing memory. At that time, the PDC primal/dual algorithm could be comparable to today's best algorithms, IBM CLEX, Gurobi and Express. For PDC there was no alternative, as there was no commercial software for ModComp Classic, and a real-world solver was needed. The SCADA system of the Orinoco Steel Company was the last used PDC primal dual algorithm. NVIDIA is a company specializing in the development of graphics processing units, GPUs, that allow researchers and programmers to develop new algorithms or adapt them for specific purposes. Jen Hasoon Huang is an American businessman. Huang graduated from Oregon State University, and then moved to California, where he graduated from Stanford University. He is the co-founder and current president and CEO of NVIDIA. As of July 2024, he is the 11th richest person in the U.S. with an estimated net worth of $118 billion. For the Da Vinci and Einsteins of our time, NVIDIA is pioneering the development of a form of accelerated computing that is loved by the world's most demanding users, scientists, designers, artists, and gamers. Driven by the insatiable demand for better 3D graphics and the sheer volume of the gaming market, NVIDIA has turned the GPU into a computational brain, at the exciting intersection of virtual reality, high-performance computing, and artificial intelligence. Now, HI is working on developing special GPU-oriented algorithms to implement the artificial brains. Below are the features of the latest GPU offered by NVIDIA. Your understanding should help develop the implementation of OPTEX GPU. The Cray 1 was a supercomputer designed by a number of computer scientists headed by Seymour Cray for Cray Research. The first Cray 1 system was installed at the Los Alamos National Laboratory in March 1976. It is one of the most well-known and successful supercomputers in history, and one of the most powerful in its time. As technical characteristics, the first version, Cray 1A, worked with vector processors at 80 MHz, was a 64-bit system and weighed 5.5 tons, including the Freon cooling system. Despite its large size, it only had 8 MB of RAM. We could say that the Cray 1A vector processor was the origin of the GPUs that NVIDIA and other tech companies produce today. Convolutional neural networks, CNN, were created to identify images that are an area of interest for NVIDIA GPUs, as much of today's artificial intelligence is concentrated in image processing. A CNN assimilates an input or output matrix to an image. This is true when you consider that images on a computer are stored in arrays of pixels. The diagram presents an example of a network geared towards image recognition of freehand numbers. In this case, the result is a discrete indicator associated with the number read. A CNN applies a set of convolutional filters, kernels, to the input images. Each filter activates different characteristics of the images, allowing a quick and effective training. CNNs can be considered totally successful for their purpose. Now, Instead of images, we can have input and output matrices, from past experiences of an industrial, economic, or social process, that relate the input parameters to the output results of mathematical models used in the management of a company. An example is the methodology used to determine a transfer function for thermoelectric power plants, when an exact mathematical function that converts inputs and outputs is unknown for determine a coal blending strategy, CBS. Imitator is a CNN that transforms CBSs from the past and the possible mixture of the input carbon into dimensions compatible with the characteristics of the output carbon, allowing pre-trained models to determine the characteristics of the resulting carbon, and thus be able to optimize the process. Imitator's design is based on a combination of multi-head attention mechanisms and transposed convolution matrices that are used for feature extraction and input transformation. The result matches the common input dimensions required by pre-trained image classification models. This implies that artificial intelligence tools for pattern recognition, images in this case, can be used in engineering projects, if we look them as simple matrices. This extends to the AI included in NVIDIA GPUs. GPUs exhibit a distinct underlying architecture with CPUs. GPUs have significantly more computation cores than CPUs. For example, the GPU NVIDIA H100 has 7,296 double precision cores. However, unlike CPU cores, many GPU cores share the same control unit and must execute the same instruction simultaneously. As a result, the hardware design of GPUs encourages high bandwidth instead of a deep pipeline. GPUs follow the single instruction multi-data (SIMD) computational paradigm, that is, threads execute the same statement but get their own data. At the heart of GPU programming is the function kernel, a program designed to execute instructions on GPUs. When the kernel starts, the runtime configures a grid of thread blocks, each block composed of an identical number of threads. A block of threads is assigned to an available streaming multiprocessor, SM, during runtime, directing them into warps, with each warp typically encompassing a set of 32 threads. Warp is the basic unit of execution in GPUs. This does not mean that all thread blocks can run concurrently on SMs, and there are no guarantees on the order of block and warp execution. This hierarchical structure is the backbone of GPUs to encourage parallel execution between threads, which improves computational efficiency by reducing latency and increasing throughput, the data processed per unit of time. The era of neural rendering has arrived, RTX Blackwell Neural Rendering Architecture. With its revolutionary RT cores, tensor cores, and DLSS technology, the NVIDIA Turing architecture laid the foundation for a new era in graphics, combining programmable shading, real-time ray tracing, and AI algorithms to deliver realistic and physically accurate graphics for games and professional applications. Image quality has been increasing faster than Moore's law by using neural rendering, and such AI rendering techniques will continue to expand. Blackwell GB202 GPU. The full GB202 GPU includes 12 graphics processing clusters, GPCs, 96 texture processing clusters, TPCs, 192 streaming multiprocessors, SMs, and a 512-bit memory interface with 1632-bit memory controllers. The GB202 GPU also includes 384 FP64 cores, 2 per SM, which are not depicted in the above diagram. The FP64 flop rate is 1/64th the flop rate of FP32 operations. The small number of FP64 cores are included to ensure any programs with FP64 code operate correctly. Similarly, a very minimal number of FP64 tensor cores are included for program correctness. The GPC is the dominant high-level hardware block within all GB20X Blackwell family GPUs, with all the key graphics processing units residing within a GPC. Each GPC includes a dedicated raster engine, 2 raster operations, ROPs, partitions, with each partition containing 8 individual ROP units, and 8 TPCs. Each TPC includes 1 polymorph engine and 2 SMs. The NVIDIA Streaming Multiprocessor, SM, is a core component of the NVIDIA GPU architecture, playing a key role in the GPU parallel processing capabilities, enabling massive parallelism through its various cores, CUDA, tensor, RT, efficient warp scheduling, memory management, and support for modern workloads like AI. Each full GB202 chip contains 192 SMs, and each SM includes 128 CUDA cores, 1 Blackwell 4th generation RT core, 4 Blackwell 5th generation tensor cores, 4 texture units, a 256 kilobytes register file, and 128 kilobytes of L1/shared memory, which can be configured for different memory sizes depending on the needs of the graphics and compute workloads. GDDR7 is the new ultra-low voltage GDDR memory standard that uses PAM3, pulse amplitude modulation, signaling technology, enabling a substantial advancement in high-speed memory design. The GeForce RTX 5090 ships with 28 gigabits per second GDDR7 memory and delivers 1.792 terabytes per second peak memory bandwidth, while the GeForce RTX 5080 ships with 30 gigabits per second GDDR7 memory, delivering 960 gigabytes per second of peak memory bandwidth. The transition from PAM4 signaling, 4 levels delivering 2 bits per cycle, to PAM3 signaling, 3 levels delivering 1.5 bits per cycle, in GDDR7, achieves a significantly improved signal-to-noise ratio, SNR. This evolution also doubles the number of independent channels with minimal I/O density overhead. These advancements also enable notable improvements in energy efficiency, offering superior performance and extended battery life, particularly in power-constrained systems. Tensor cores are specialized high-performance compute cores that are tailored for the matrix multiply and accumulate math operations that are used in AI applications. They provide groundbreaking performance for the matrix computations that are critical for both deep learning, neural network training, and inference operations. Generative AI models have improved in capabilities since the first ones, released in 2022. But the improvements have often come with an increase in parameters and size. As models grow in both compute and memory requirements, it can be difficult to run such models even on the latest hardware. FP4 allows virtually no loss in quality with advanced quantization methods offered by the NVIDIA TensorRT Model Optimizer, a comprehensive library of state-of-the-art post-training and training-in-the-loop model optimization techniques. These techniques include quantization and sparsity to reduce model complexity, enabling downstream inference libraries like NVIDIA TensorRT LLM to more efficiently optimize the inference speed of deep learning models. Games today are more realistic than ever, with richly detailed worlds and high-quality visual effects. Ray tracing enables physically accurate lighting, shadows, and reflections, creating virtual environments that closely mirror reality. Developers also enhance games by increasing geometric detail and using various advanced shading techniques. NVIDIA has enhanced several important features of the RT core to enable high-performance ray tracing of highly complex geometry, like intersecting box engine, triangular group intersection engine, linear scan spheres, opacity micromap engine, and triangular cluster compression engine. Megageometry provides new bounding volume hierarchy, BVH, construction capabilities that adopt cluster-level acceleration structures, CLAS, of triangles, as first-class primitives can be generated from spatially compact batches of up to 256 triangles. A collection of claws is then used as input to construct a final BVH. Claws can be generated on demand, for example, when an object is loaded from disk, and can then be cached for future frames. Because each class represents a collection on the order of 100 triangles, the processing required by subsequent BVH builds is reduced by 2 orders of magnitude compared to classic triangle-based methods. Consequently, a game engine can budget for many more BVH builds per frame, and handle cluster load switches by simply reconstructing the BVHs of affected objects from class S. To address this, Megageometry introduces a new type of PLUS called a partition top-level acceleration structure, PLAS. Instead of building a new PLUS from scratch every frame, PLAS can exploit the fact that most objects in the scene are static from one frame to the next. The application manages a persistent PLAS object by aggregating objects into partitions and updating only those that have changed. Shader execution reordering, SER, is a powerful technology that lets ray tracing applications efficiently reorganize the massively parallel threads on a GPU for maximum hardware utilization. Dynamically reordering work with SAR is particularly effective in challenging ray tracing workloads that exhibit large amounts of execution or memory access divergence, such as path tracing. Because threads that coherently execute neural workloads can be sent directly to the tensor cores, SAR also significantly accelerates neural shading. The AI Management Processor, AMP, is a fully GPU programmable context scheduler designed to offload GPU context programming from the system's CPU. It is divided into two functions, the first aimed at game engine, and the second, at LLM models. The AMP is implemented using a dedicated RISC-V processor located at the front of the GPU pipeline, and it provides faster scheduling of GPU contexts with lower latency than prior CPU-driven methods. AMP improves GPU context scheduling in Windows to more efficiently manage different workloads running on the GPU, using RT Core, CUDA Core, and Tensor Core. Essentially, AMP is used to coordinate, schedule fairly, and ensure a smoother gaming experience without performance drops. With LLM, it reduces the time to first response, and with games, it prioritizes working with the game engine to avoid stuttering. By delivering work at more predictable times, AMP can significantly improve quality of service based on workloads. NVIDIA DLSS super resolution and frame generation technologies have increased frame rates dramatically, while often delivering native rendering level image quality and generating most pixels at a fraction of the cost of traditional rendering. The AI Management Processor enables better programming of DLSS AI processing, graphics rendering, and frame rate algorithm. DLSS is a revolutionary suite of neural rendering technologies that uses AI to boost FPS, reduce latency, and improve image quality. The latest version, DLSS 4, brings new multi-frame generation, manufacturing, with faster performance and lower memory usage, and a new transformer model containing advancements for super resolution, SR, ray reconstruction, RR, and deep learning anti-aliasing, DLAA, that enhances image quality and stability. As a further improvement to existing ray tracing solutions, all megageometry APIs are designed to be fully batched, with their input parameters driven entirely from GPU memory. This lets the game engine run logic like modern level of detail, LOD, selection, animation, culling, and others efficiently on the GPU, while minimizing round trips to the CPU. With effective use of megageometry APIs, an application can practically eliminate CPU overhead related to bounding volume hierarchy, BVH, management. In this case, the image of the crab is handled as a finite element structure discovered by megageometry. Finite elements and differences are structures commonly used in engineering, and in many dynamical mathematical models they can be associated with the change of the decision and state variables of the system being modeled, which represents the gradient of these variables. HI is exploring the use that can be given to megageometry for the evaluation and visualization of the results of a dynamic mathematical model. This is directly related to visualization through digital twins. Like the fact that NVIDIA has developed tools to manage predictive artificial intelligence in GPUs, looking to the future, HI believes that one of the next steps is to develop optimization-oriented intelligence, or prescriptive artificial intelligence, thinking that it is a future that is beginning to develop. The first step is to demonstrate that, in the current state of technology, GPUs are already a solution that surpasses conventional optimization. This is HI's vision, supported by its experience and the research already carried out by several scientists in the area. A lot of competition is coming after NVIDIA's dominant position, therefore, it is possible that other companies will receive a boost from AI. NVIDIA is revolutionizing Intel, that's for sure, just like ARM Limited Advanced Micro Devices Incorporated is competing head-on with both companies and has done an incredible job of bringing AMD back to prominence. All cloud players are developing silicon, as is IBM Corporation. Broadcom is vying for commercial silicon share and is focusing on surrounding components, including smart NICs, along with Marvell and connectivity. Other players are developing semiconductor capabilities, such as Apple, Tesla, and Meta Platforms Incorporated, and finally, Chinese companies are designing and manufacturing silicon chips to achieve independence. Therefore, NVIDIA is far from alone in this market, but it has a huge advantage. The Central Processing Unit, CPU, is the brain of the computer, providing the instructions and processing power to do its job. To give these instructions, a CPU must be able to think quickly, so CPUs are equipped with a large amount of cache memory. The CPUs are equipped with multiple cores. These cores make use of the cache to reduce latency, allowing the CPU to process instructions provided by applications faster. This makes a CPU good at serial processing, and can simulate parallel processing, applying round-robin CPU management policies. Today, a graphic processing unit, GPU, is designed to handle work related to images, such as graphics, effects, and videos. To be effective, a GPU must be able to handle a large amount of data at the same time. The GPU must have high performance. For example, when you're gaming, you want to maximize the frame rate, FPS, to allow for a smoother gaming experience. GPUs do this by breaking down problems into thousands or sometimes millions of separate tasks and solving them at once. This is called parallel processing, and that's why GPUs are equipped with hundreds or even thousands of more specialized cores, giving GPUs the high performance they need. The image shows the architecture of the CPU and GPU. A CPU has a lot more cache compared to the GPU. This reduces the CPU's need to access slower underlying storage, such as a hard drive, and therefore reduces latency. It allows the CPU to think faster. The image also shows that a GPU consists of many more cores than a CPU, the green squares. These cores are less powerful than the cores used in a CPU, but they allow the GPU to perform similar calculations in a parallel data stream. Traditionally, optimization problems are solved by making use of the power of CPUs, ignoring the possibility of working with GPUs. However, the current power of GPUs, and the evolution of thinking around algorithm design, allows us to explore other possibilities, whose experiments have already shown that this is totally viable. Some cases reported in the literature are analyzed below. Linear programming problems consist of maximizing, or minimizing, a linear objective function subject to a set of linear constraints. Below is the basic version of the simplex method, invented by George Dantzig in 1947. This method seeks the solution by moving through iterations that move between vertices of the feasible region, which is why it has been called the outer point method. There are two basic versions of the simplex method, the standard and revised. The revised simplex method is generally more efficient than the standard simplex method for large linear programming problems, but for dense LP problems, the two approaches are equivalent. Dense linear programming problems occur in many important domains. Some decomposition methods, such as Bender's and Dantzig-Wolfe, result in complete dense LP problems. Exterior point linear programming algorithms. In linear programming, primal and dual methods are two complementary approaches to solving the optimization problem. The primal method focuses on finding the optimal solution directly from the original formulation of the problem, while the dual method is based on solving a related transformed problem based on the theory of duality. Primal simplex method. It is the traditional method for solving linear programming problems. Start with an initial feasible solution and iteratively seek to improve it until optimal is reached. It is used when you have a feasible initial solution. Dual simplex method. It is used when there is a solution that satisfies the optimality of the objective function. It is called dual feasible, but is not feasible for the original constraints, primal unviable. It is useful when working with problems where primal feasibility is more difficult to satisfy than dual feasibility. Primal dual simplex method. It combines the advantages of both methods to improve efficiency in solving linear programming problems. It can be more efficient in certain types of problems, especially those with high dimension or degeneracy. The method uses a point that is feasible and optimal simultaneously, using iterations that improve the solution in both aspects. The paper. Efficient implementation of the simplex method on a CPU-GPU system. And the paper. Multi-GPU implementation of the simplex algorithm. proposes its implementation through Compute Unified Device Architecture, CUDA, in a multi-GPU architecture. NVIDIA introduced CUDA in 2006, a software technology that allows users to solve many complex problems with their GPU cards. NVIDIA GPUs are SIMD, single instruction, multi-threaded, architectures, in which different threads simultaneously execute the same. They are particularly suitable for addressing problems that can be expressed as parallel data calculations. A grid represents a set of blocks where each block contains up to 1024 threads. A grid is launched from the host, CPU, via a kernel program. When the kernel is used, the execution is moved to a GPU. When all kernel threads complete their execution, the corresponding grid ends, and execution continues on the host until another kernel is invoked. When a kernel is released, each multiprocessor processes a block by executing threads in a group of 32 parallel threads called warps. The threads that make up a strain start together in the same program direction but are free to branch out and run independently. As thread blocks are terminated, new blocks are started on idle multiprocessors. With CUDA 3.0, threads in different blocks cannot communicate with each other explicitly, but they can share their results through global memory. As thread blocks are terminated, new blocks are started on idle multiprocessors. With CUDA 3.0, threads in different blocks cannot communicate with each other explicitly, but they can share their results through global memory. When implementing the simplex method, most of the time is spent on pivot operations. To speed up the process, simplex tableau breaks down. We denote by I the number of available GPUs. This step involves m+1 times n+1 double precision multiplications, and m+1 times n+1 double precision subtractions that can be parallelized on the I GPU so that each GPU updates a part in each iteration. The proposed implementation is based on the simultaneous implementation of identical CPU threads, so that each GPU I is managed by its own thread on the CPU. Therefore, the CPU thread is made up of 4 kernels required by the simplex algorithm, and these 4 kernels are executed by the ith GPU. This approach allows the context of each CPU thread to be maintained throughout the application, so CPU threads are not deleted at the end of each iteration of the simplex algorithm. As a result, communications are minimized. The solver GPU chose to horizontally split the simplex tableau as this decomposition allows the theta ratio column and the incoming variable column to be processed in parallel between all GPUs. The output variable line is computed by a single GPU in each iteration. Each block of dimension 16 by 32, a column of 16 items of the output index k is loaded into a shared memory of some GPU. The blocks then process the corresponding part of the simplex tableau independently, in parallel, in the GPUs, as the thread, x, y, of the block, x, y. Below is presented the simplex algorithm on a CPU-GPU system. Incoming or outgoing variables are the result of searching for a minimum value within a set of values calculated in GPUs. This can be done on the GPU through reduction techniques. However, experiments get better performance by performing this step sequentially on the CPU. In fact, the size of the problems and double precision operations lead to the worst efficiency for the parallel approach. In addition, CUDA does not support double precision operations. The process consists of the following steps. In step 1 of the simplex algorithm, the first line of the simplex tableau is simply communicated to the CPU. However, step 2 requires processing a column of proportions. This is done in parallel by kernel 1 and the ratio column is communicated to the CPU. Since step 3 requires column k, the input column of the simplex box variable, kernel 1 is also used to get the old column k and store it in CPU memory to avoid memory conflicts. The image shows the processing times for the different sizes of LP problems, for sequential and parallel algorithms. We can see that, for each LP problem size, the dispersion of processing time is low. Although the processing time increases with the problem, the parallel algorithm, CPU-GPU, is always faster than the sequential algorithm, CPU. The table shows two indicators of the gain in speed due to the use of PIS, speed up 1 CPU versus 1 PU, and speed up 2 PU versus 2 PU. Both speed up 1 and speed up 2 increase with the size of the problems. For small size problems, for example 1000 by 1000, the speed up 1 is relatively small, average equal to 2.93 times. Because the GPU power is lightly exploited, this gain can reach 12.74 times, for large instances. Speed up 2 indicates an additional gain that reaches an additional level of around 1.93, the ideal level is 2, which shows that using 2 GPUs leads to a very small loss of efficiency for large problems. The total speed 1 would be 24.5 times. This confirms the advantage of the proposed approach, as the use of multiple GPUs allows large problems to be solved efficiently, in a reasonable processing time. The multi-GPU implementation of the simplex method is realized via CUDA, Compute Unified Device Architecture of NVIDIA for GPUs. The computational results were obtained with a system with 1 CPU and 2 GPUs. The CPU was a 2.66 GHz Xeon E5640 and 2 NVIDIA Tesla C2050 GPUs. CUDA 3.2, Compute Unified Device Architecture of NVIDIA for GPUs, was used for the parallel code and GCC for the serial code. Computational tests were carried out on randomly generated instances for non-sparse LP problems. Displays processing times for different sizes of LP problems and for sequential, blue, and parallel algorithms red and green. Parallel algorithms, with 1 and 2 GPUs, are always faster than the sequential algorithm. In the sequential case, for issues of size 8000 by 8000 the processing time exceeds the 16-hour limit. The tests show a maximum speedup of 24.5 with 2 Tesla C2050 boards. This research demonstrates the effectiveness of the methodology. Julia is a high-level, general-purpose dynamic programming language. Julia is designed to be fast and productive for data science, artificial intelligence, machine learning, modeling, and simulation, and is mostly used for numerical analysis and computational science. Distinctive aspects of Julia's design include a type system with parametric polymorphism and the use of multi-send as a core programming paradigm, a default just-in-time (JIT) compiler, with support for early compilation, and an efficient, multi-threaded, garbage collection implementation. Julia does not support classes with encapsulated methods and instead relies on structures with generic methods not linked to them. Julia runs similarly to scripting languages, using their runtime, and allows interactions, but Julia programs can also be optionally sent to users in a ready-to-install execution file, which can be done quickly, without the need for pre-installed code. The commercial solver companies, such as Gurobi, try to use GPUs to speed up their solvers, but the early efforts were unsuccessful. The fundamental reason is that GPUs do not work well for solving sparse linear systems, which is the computational bottleneck of simplex or barrier method solving LP. The restarted primal dual hybrid gradient, PDHG, is a GPU implementation to solve LP. The design of CUPLP JL is illustrated in the figure. To avoid costly data transfers between the CPU and GPU, CUPLP JL runs as much as possible on the GPU and is not oriented to a spare linear array. Only 2 CPU-GPU communications are required for CUPLP JL. One transfers the scaled LP instance after preconditioning from the CPU to the GPU, while the other moves the final solution from the GPU to the CPU as output. The main iterations run entirely on the GPU, and there is no need to transfer any vectors before termination to alleviate expensive CPU-GPU communication. The figure shows the number of instances solved by CUPLP JL and 3 Gurobi methods in MIP relaxations at a given time, without using the presolve option. One observation is that the number of instances that Gurobi can resolve for a given runtime does not differ much for moderate and high accuracy. On the contrary, this difference is more evident in the case of CUPLP JL. This is a feature of a solver based on first-order methods. It should be noted that CUPLP JL has a computational overhead of around 1 second due to the GPU kernel release time. The figure shows the number of instances solved by CUPLP. JL and 3 Gurobi methods in MIP relaxations at a given time, without using the presolve option. One observation is that the number of instances that Gurobi can resolve for a given runtime does not differ much for moderate and high accuracy. On the contrary, this difference is more evident in the case of CUPLP. JL. This is a feature of a solver based on first-order methods. It should be noted that CUPLP JL has a computational overhead of around 1 second due to the GPU kernel release time. The figure shows the number of solved instances of CUPLP JL and 3 PDLP implementations that use different threads. As shown in both panels, CUPLP JL has significantly higher performance than all PDLP CPU versions, regardless of accuracy. Deploying multiple GPUs uses some communications to synchronize GPUs, which depend on how the problem is spread across GPUs. The process is: the constraint matrix is divided vertically to minimize communication. After preparing the problem, the CPU creates threads that will manage the GPUs. Each of them then initializes its GPU and loads a subarray into its gram. During an iteration, each CPU thread simultaneously launches the steeper edge kernel to get a local input variable. This is where the first communication comes in. Each GPU must share its local result with the others. They then narrow down the local result to choose the same optimal input variable. Because of the selected split, only the CPU thread that contains the input variable launches the expansion kernels to select the output variable. The column of this variable, called the pivot column, is required for all other GPUs to execute the pivot step. Therefore, this column, along with the output variable, is transmitted, and finally, each GPU prepares and launches the pivoting kernel without further communication. Note that GPUs communicate with each other through CPU threads. The test environment was configured as CLP, a sequential implementation of the revised simplex method, was chosen for the comparative tests between a standard solver and GPU solvers, using the netlib problem repository. CPU server, 2 Xeon X5570, 2.93 GHz, with 24 GB of DDR3 RAM, and a GPU computer system, NVIDIA Tesla S1070, connecting 4 GPUs. Each GPU has 4 GB GDDR3 graphics memory, 30 streaming multiprocessors, each holding 8 processors, 1.4 GHz. One GPU delivers a maximum throughput of 1 flops for single precision floating point, 80 flops for double precision floating point, and a memory bandwidth of 100 GB per second between threads and gram. A time limit of 1,250 seconds was imposed. As shown for large enough issues, constraints greater than 750 and variables greater than 3,750, GPU implementation substantially outperform CLP. A time limit of 1,250 seconds was imposed. However, with small issues, CLP is more efficient, which is normal due to technology overload, but CLP continuously grows and explodes when the problem size grows above 750 constraints. Implementations of the revised simplex method are strongly influenced by the density of the array. The denser the problem, the slower the CLP will run. However, to dig deeper into how these deployments behave under various densities, we measure the execution time in a fixed size problem, 500 by 2000, but with an increasing density. Finally, the GPU solver was validated by calculating the correlation between the measurements and the 1 to 4 GPU models, which was above 0.999. For very large problems, constraints greater than 5,000 and variables greater than 25,000, the predicted acceleration is almost optimal up to 40 GPUs. The figure shows the number of solved instances of CUPLP JL and 3 PDLP implementations that use different threads. As shown in both panels, CUPLP JL has significantly higher performance than all PDLP CPU versions, regardless of accuracy. Design of the OPTEX GPU, the artificial brain solver. As George Bernard Shaw would say, imagination is the beginning of creation. You imagine what you desire, you will what you imagine, and at last you create what you will. Thank you very much for your attention.